Welcome to Virtual Science. Today's content is about harmonic oscillator. Harmonic oscillator is very important to study various branches of physics. Even it plays a vital role in explaining different vibrational phenomena. So, what is the classical concept of harmonic motion? Classical mechanics shows that harmonic oscillator is a motion that appears when a body is displaced from its equilibrium position and the body experiences a restoring force proportional to its displacement. That means, suppose I have a particle at x equals to 0, the mass of the particle is m, and somehow this is in equilibrium position. Somehow I am disturbing the particle. That means by applying force or something, this particle goes to at x. So if the particle experiences a restoring force, that means the particle is forward direction and its force, if its force acts as a reverse direction, that means it's always a restoring force, negative sign, and the force is proportional to the distance or displacement, then we can say that the particle is in harmonic motion or harmonic oscillation. That means F equals to minus kx, where k is the constant or k positive constant. This indicates that the position of the force experience on the particle is always depends on only on its distance and always negative to the direction of the motion. And where k is the force constant, and k, the value of k can be found out from its angular frequency. That means angular frequency is written as square root of k by m, where m is the mass of the particle. And from this equation we can easily write down that the potential of this particle for this motion is half m omega square x square, because if can be written as minus grad v, v is the potential, or in one dimensional case we can write that f equals to minus del x, and after integrating we can find out the potential of the harmonic oscillation. So what happens for quantum particle? That means if the particle is very teeny, what happens for it? Actually, in quantum mechanics also, the particle experiences the force Vx. The particle experiences the potential Vx equals to half m omega square x square. So if we consider the quantum particle, that means teeny particles, we have to write down the Schrodinger's equation first and then try to solve this equation. So let's write down the Schrodinger's equation for the particle in harmonic oscillation. Schrodinger's equation can be written as minus h square by 2m d2 psi dx square plus, I am putting the value of Vx equals to half m omega square x square psi equals to psi, where psi is a function of only x, and I am considering here only one dimensional case. That is why grad square psi becomes del square del x square, and as psi is only function of x, then del square psi del x square equals to del 2 d2 psi dx square, as we have discussed earlier. So this can be written as d2 psi dx square plus 2me by h square minus m square h square x square by h square into psi equals to 0. This is the Schrodinger's equation for the particle in harmonic oscillation. So we have to find out psi, that means the wave function of the particle of harmonic oscillator, and again also have to find out the energy E. That means our main job is to find psi and E. And to find out the psi, we have to first solve this differential equation. This differential equation can be solved by two ways. One is analytical way analytical way, and another one is algebraic way. Analytical way means by assuming power series method, by using power series method, and algebraic means later I am solving this differential equation by both the way. First I will discuss by analytical method, then algebraic method. I am writing here the differential equation again. This is my differential equation, and I am considering that y equals to square root of m omega by h cut into x, and again I can consider m omega by h cut equals to alpha. This is for my simplicity, so I can write this is square root of alpha, then dy dx goes to square root of alpha. Now I am interested to find d2 psi dx square. So first d psi dx gives us d psi dy dx, that means square root of alpha d psi dy, and again if I and the derivative with respect to x, then this will gives us d dx of d psi dx. This can be written as d dy of d psi dx into dy dx, and d dy of d psi dx, that means square root of alpha d psi dy into dy dx means square root of alpha, that means this will gives us alpha d2 psi dy square. So I am now putting the value of d2 psi dx square and also a value of x, and after a step I can easily write down that e by h cut omega minus y square psi equals to 0. Again, for my simplicity, I am assuming that where k equals to 2e by h cut omega, I have reduced the differential equation from this equation, that means from equation 1 to equation 2. Okay. Now I have to assume something. Wave function is finite. We know this, that wave function is finite at every step. That is, wave function is finite even if x equals to infinity. I am considering x first. Okay. And at x tends to infinity, that means y tends to infinity. At y tends to infinity, psi is finite. Y tends to infinity means e tends to 0. That means k tends to 0. That means we can write the differential equation number 2 as this is a trivial differential equation, and its solution can be written as psi equals to f of y e to the power minus y square by 2, because y square psi y, and this is a double derivative, this will goes to a Gaussian shape function e to the power minus y square by 2, and f of y is some unknown function which depends on only y, and our job is to find f of y. If you have any questions how this equation goes to this equation, that means how psi is the what is the value of psi, if there is any confusion, please let us know, we will clarify it later. So our main job is now to find phi f of y, that means a polynomial function. So we have considered psi equals to f of y e to the power minus y square by 2. Now our job is to find d2 psi dy2. I have to find it. That means d psi dy, I have to find first d psi dy. This will goes to f of y e to the power minus y square by 2 minus y plus df dy e to the power minus y square by 2. I am doing nothing but just doing this difference and derivative differentiation, because ddx of uv, if u and v are the function of x, then we can write du dx at v plus u dv dx. I think you all know this from intermediate. So d2 psi dy square can be written as f of y square e to the power minus y square by 2 minus 2 df dy into y e to the power minus y square by 2 minus f of y e to the power minus y square by 2 plus d2f dy2 e to the power minus y square by 2. Now I am putting this equation to my second equation. That means d2 psi dy2 plus k minus y square. I am putting the value of d2 psi dy2 and psi in this equation, because this is our main prime equation obtained from Schrodinger's equation. I have assumed k tends to 0 to find some polynomial function and some uh, function dependent of y for the finding value of psi. So putting the value of d2 psi dy2 and psi in this equation, and after a few steps, that means after simplifying, we can easily write down d2 f dy2 minus 2y df dy plus k minus 1 into f of y multiplied by e to the power minus y square by 2 equals to 0. Just put the value of d2 psi dy2 and psi. Psi means f of y e to the power minus y square by 2 in this equation. That means, okay, put the value of psi in this equation. So finally what we have got, d2 psi dx square minus 2y df dy plus k minus 1. This is 0. So we have started our job by doing some motivation that we have to find the function. That means we have to solve the differential equation first, and we have reached finally again and another differential equation. So you can think that this is a tedious job. That means our main job was to find out psi, and otherwise finding the psi, I am deriving another differential equation. This is not possible, but this is the only one way to solve this equation. Now interesting case arises, because this equation looks like another equation. I am writing here d2y dx square minus 2x dy dx plus 2ny equals to 0. Suppose this is a differential equation, y depends on x only, n is the constant, then this differential equation was solved by Hermite, and this is called Hermite polynomial, and this is denoted as h n x. Hermite polynomial is written, this is minus 1 whole to the power n e to the power x squared ddn dxn e to the power minus x square. This is the Hermite polynomial, and the solution of this differential equation is y equals to some constant into Hermite polynomial. Okay, and so this equation, what we have got, this equation resembles to this equation. If we put k minus 1 equals to 2n, that means if we put k equals to 2n plus 1, then our equation looks like Hermite equation, and we can easily solve this equation by doing f of y equals to some constant a into h n y. The condition for this is k equals to 2n plus 1. Now I am considering that k equals to 2n plus 1. So f of y equals to a h n y. So what we have got, that we have assumed psi of y equals to f of y e to the power minus y square by 2, and k equals to 2e by h cut omega, and we have finally got that f of y equals to a Hermite polynomial and k equals to 2n plus 1. So I can find out psi of y equals to a h n y e to the power minus y square by 2, and psi of x equals to a h n square root of alpha x e to the power minus alpha x square by 2, because I have assumed y equals to square root of alpha into x, and our final job is to find psi x, because I have considered the x direction only. So this is our final equation, final solution of differential equation of Schrodinger equation for the particle moving in one dimensional case in harmonic oscillation. So this is our wave function. So what is the case of energy? This k equals to 2e by h cut omega equals to 2n plus 1. That means energy equals to n plus half h cut omega. I am putting the En, that is En is the energy of n state. So if n varies from 0, 1, 2, this is always positive direction, because in Hermite polynomial n is not positive. So this is the equation of energy of the particle in harmonic oscillation in quantum mechanics. Okay, now our job is to find out the constant, normalization constant a. To find out a, what we have done, actually for the normalization constant we have to normalize the wave function minus infinity to infinity. That means if I put the value of this here, this will go as square root of alpha x e to the power minus alpha x square dx equals to 1. So again difficulties arises in this equation, but interestingly there is solution. We have write down the Hermite polynomial, Hermite equation, and Hermite polynomial holds good some relationship, and one of the common is if integration holds from minus infinity to infinity to the power minus x square h mx multiplied by h mx dx This goes to 0 for m not equals to n, and this goes to 2 to the power n factorial. This is the orthogonalization of the Harmonic polynomial. So from this equation we can easily find out the value of a, and the value of a looks like this equation finally gives us 2 to the power n factorial square root of pi by root alpha equals to 1, because alpha x square, alpha exists here, and again we have to assume that square root of alpha x equals to y, and putting the value we can easily find out this. If you have any problem, please contact us. So finally a equals to alpha by pi whole to the power 1 by 4 square 1 by square root of 2 to the power n into n factorial. So finally we have able to find out the wave function of the harmonic oscillator particle. Psi m equals to alpha by pi whole to the power 1 by 4 1 by square root of 2 to the power n into n factorial h n of square e to the power minus alpha x square by 2. H n x is the Hermite polynomial, and alpha equals to m omega by h cut. And we have already derived the energy of the particle as n plus half h cut omega, where n varies from 0, 1, 2, etc. So this is the wave function. This is wave function of the particle moving in harmonic oscillation, and this is the energy. So now we are interested to find out some sketch of the wave function as well as the probability density. So this blue line indicates that, sorry, this green line is the potential. This is psi x, this is psi x. Green line indicates the potential, and the blue line is this is the ground state wave function. And how can we measure the ground state? If we put the value of n equals to 0, putting n equals to 0, this is for ground state. N equals to 1 gives us first excited state, n equals to 2 gives us second excited state, and that's all. So from Hermite polynomial we can write down that h01 x equals to 1, h1x equals to x, h2x equals to x square minus 1, and that's all. So ground state wave function can be written as alpha by pi whole to the power 1 by 4 e to the power minus alpha x square by 2, where alpha equals to m omega by h cut. This ground state is very much important to derive some mathematical calculations, and in this case blue line indicates the ground state wave function, and here at the right side this indicates the probability density. The yellow line indicates the first excited states, and the red line indicates the second excited states. So this harmonic oscillator and having energy, ground state energy E0 or E naught equals to half h cut. This is consistent with Heisenberg uncertainty principle. So let's check how this follows Heisenberg uncertainty principle. So we have already derived, or we know that delta p delta x equals to h cut by 2. This is Heisenberg uncertainty principle. So if the and I am now interested what happens for harmonic oscillation. Actually energy of the harmonic oscillator E equals to p square by 2m plus half m omega square x square. So the minimum energy must be delta p square by 2m plus half m omega square delta x square, because delta p is the error or minimum value of the linear momentum and delta x is the error or deviation or minimum value of the position. So minimum energy can be written as by this equation. So I am just replacing delta p equals to h cut by 2 delta x, that means h cut square by 8 m delta x square plus half m omega square delta x square. I am doing nothing but from here we can easily write down h cut by 2 delta x. This is the minimum value. So for stable minimum value we have to derive or derivative this must be 0, that means h cut square by 8 m into 1 by x square, that means minus into delta x to the power cube plus m omega square delta x equals to 0. That means, so finally we can write that delta x equals to square root of h cut by 2 m omega. That means delta p equals to h cut by 2 into 2 m omega by h cut. That means m omega h cut by 2. Now if I put the value of delta p and delta x in the value of em, that means in this equation, we will find again that this is equals to half h cut omega. So the minimum energy half h cut omega, this is consistent with Heisenberg uncertainty principle, and this energy indicates that even if the particle is raised, the energy, there is some minimum energy, this is half h cut omega, and even if the temperature of the system is 0, then this will also be non-zero minimum energy. This is consistent with Heisenberg uncertainty principle. More will be discussed in the next class. Please subscribe our channel and comment in the comment box, and for further query please mail us at farsighteach@gmail.com. Thank you.